Hello everyone, and welcome to the NEATEC Electronics Series. This episode is about the diode, so let's get started. Alright everyone, let's talk about the diode. Now I drew one for you here, and I want to make sure that you have some information about it so you understand what is going on here. So remember, your PN junction with the holes, that's on this side right here. I denoted it with a blue P, okay? The N-type region with your electrons, the additional electron in the lattice, remember, your N-type region is over here on the right. Your depletion region right here, and then your barrier, well, you're gonna have a barrier here. Some texts they draw this yellow, some they draw it green. It all depends what text you're using. Alright, so now remember, you're gonna have a barrier potential, right? So on one side you're going to have a bunch of electrons. It's going to be negative, right? It's negative charge. And on the other side, you're going to have some holes, right? So it's going to be positive. Now there you go, all right? So with a diode, I want to make sure that you understand that the symbol is given to you right here. This is what you have as a diode. Notice it's like an arrow. By the way, this sometimes is filled in. It's simply dark, just like this, okay? It's an arrow, and it's pointing to the N region. Now listen to this. Make sure you understand it, because everyone gets confused on this. The arrow is pointing to the right, to the N region. When most text, not all, but most text reference the diode using conventional current flow. Now, if you think of a battery has a plus terminal and it has a minus terminal, right? And you usually have a little nib here, right? Well, you're thinking of the current going from plus to minus. That's conventional current flow, all right? But remember, electrons are going in the opposite direction, all right? So I just don't want to get people confused with that. Now, the P-type region is called the anode, and the N-type region is called the cathode, all right? So now that we have this understood, let's start doing something here. Let's bias this thing, shall we? So the first thing I'm going to have to do is I'm going to have to get rid of some things here, right? Because we're going to bias this. Now, what do I mean when I say bias? That means what we're going to do is we're going to put a voltage on it. We're going to connect the battery to it, right? This is a resistor, R, okay? Many times a resistor is just a line and it squiggles like that. That's how many people draw a resistor. That's how I draw a resistor. Some people just simply draw a resistor like this, and they might put R on it, or the R might be over here, but you get the idea. It's simply a resistor, okay? Don't think into that too much right now. We'll go over that, what that resistor is there for, in a minute. Now, let's continue drawing this, right? We're coming over here, okay? And we're going to have this one come down and come over here. here. Now, if anyone there has ever jumped a car battery, usually, okay, it's plus to plus, minus to minus. So that's what I'm going to show you first, okay? Now, how I have this set up here, if this is your battery, now let me show you the symbol for the battery. It's a small, it's larger, small, larger. Depending on how many, you can have as many of these as you want. Lines are what I'm talking about, and it ends on a longer line. So this will be the positive, and this will be the negative. It's simply a battery. And how it's connected now, this is called forward bias. All right? That's what that means. So now let's be clear about this. Remember what we said. We have a barrier potential here, don't we? So we have to have enough pressure. I call voltage pressure. I could say voltage. The voltage of the forward bias must be greater than the barrier potential. If this diode is made of silicon, I'm going to draw it over here, just silicon. We know that that barrier potential, right? I'm just going to say here barrier potential equals 0.7 volts. Get it? That means there must be at least 0.7, more than 0.7 volts for electrons to have enough energy, right? You have an electron coming in here to have enough energy to get across this barrier. Because remember, this negative charge over here repels electrons, right? So you have to have additional energy for them to get over here. Now, to get over the barrier and into the P region, okay? So let's think about this a little bit deeper. This is important that we understand exactly what's going on, because you're going to have a free electron here, right? This, in the N region, you're going to have free electrons in the conduction band, okay? Say free electrons. And they are in the conduction band. Now look, I want to say something. We say in the conduction band, that refers to energy. Sometimes you hear it's called the conduction shell. You have the valence shell and the conduction shell. So they have to have enough energy to jump from the valence shell into the conduction shell, which means they're free. They aren't held by any atom, okay? So they can move. And if they have enough energy, they're going to then move. This is electron current on this side, right? Remember that. This is, I'm going to have to put something else over here. This is going to be electron current. That is the movement of electrons in the conduction band, okay? So, they're in the valence band. They have enough energy based on this forward bias. They jump out of the valence band into the conduction band, and then they have enough energy to get over this junction. Once over the junction, that junction is taking energy, right? 0.7 volts. So what they're going to do is they're going to drop down, and here on this side they're going to go back into the valence band, and you're going to have what is termed as hole current. Got it? Electrons in the conduction band, they go across the barrier, they lose energy, they drop into the valence band, and here you have hole current. Now look, you have an electron here. Electrons are going to be attracted to this side because it's positive, right? Electron's negative. So at this point, it's going to be attracted here, so your electrons, I'm going to put the electron in red, right? It's going to go this way, right? That's your electron, right? A little bit of minus sign there. What's going to happen to your holes? Where are they going to go? Remember, you're in the valence band. This is hole current, and your holes are going to go in the opposite direction of your electrons. They're going to go this way. I'm going to denote that as an H. Okay? Then when the electron gets over here, this is a metal connector. And once it does that, the electron can simply flow to your battery. Now, what this resistor does is this is going to limit the current. If you don't have this in here, you can burn out your diode, all right? Because there is a limit to how much current you can flow through a diode without damaging it, okay? It will get too hot and just burn. So that is why you need that resistor. So as I was saying earlier, electrons that make it this far, they then enter the conductor. They become free electrons in the conductor. If you recall, the free electrons and valence electrons in metals, their energy bands overlap. So they are based, you can think of them as in the conduction band, and they will conduct all the way through here back to your battery. Okay? Now, the other thing to think about here, what do you think is going to happen to your depletion region? In your depletion region, right, if you're forward biased, and this side as we drew it is going to have positive charge here, right? And you're going to have what? Negative charge here, right? Now remember, you're going to have a large number of electrons. Since this is connected, this is your N region, right? I'm put a little N here for you. You're going to have a large number of electrons because this is connected to the negative part of your battery, as shown right here, all right? It's connected to the negative part of your battery, right? So you're going to have a large number of electrons coming in. Well, the more you put in here, what's going to happen? You have a positive charge right here. It's going to fill some of these holes. All right? On the other side, right, you have a positive on this side, on your left side. So some of these electrons are going to be attracted to that, so you're going to lose electrons. So the net effect here is this depletion region is going to narrow. So as more electrons flow into the depletion region, the number of positive ions is reduced. As more holes flow into the depletion region, the number of negative ions is reduced. And this basically is what causes the depletion region to narrow. That's what I was trying to say. So that is what happens when you have a forward bias. And remember, if your barrier potential, if this bias you have right here, this battery, if the voltage is less than 0.7 volts for silicon, assuming that's a silicon diode, you're not going to have enough energy for these electrons to jump the barrier, to get across the barrier. So you're going to have zero current flow. It has to be above 0.7 to have any current flow. All right? All right, everyone. We're going to come back shortly, and then we're going to talk about reverse bias. See you soon. Alright everybody, let's start with the diode just like last time, but now let's reverse bias this diode, alright? So to start off, the first thing I'm going to do is get rid of non-useful things we just don't need, alright? There we go. We don't need that, right? And we can simply erase this little part of the brace. Now, let's go back to the basics, right? We need to connect this wire. It's coming through a resistor. Gonna come around. And this side coming here. Now, remember, this is reverse bias, right? So on reverse bias, you want your cathode positive biased and your anode negative biased. And if I'm going to draw the battery, it would be small, long, small, long, small, long. It comes right back here, okay? That diode now is reversed biased, okay? So let's just think, what's going to happen here? In this N region, right, you have an extra electron in the lattice. These electrons, I'm going to draw one up here, it's going to be pulled this way, isn't it? When it's pulled this way, that means that this part, remember, this part of your junction is lined with a positive charge, isn't it? It's going to be pulled this way, isn't it? It's exactly what's going to happen. Because remember, when electrons leave that part of the lattice, it's going to leave it with a negative charge, or positive charge, isn't it? What's going to happen on the other side? Well, basically, on this side, let me get the red here. You remember, you have a line of negative charge here along your depletion region, right? Now when you apply a negative voltage to this, okay, what's going to happen? Electrons are going to enter the valence band and migrate to the p-n junction. Electrons are going to migrate, that's an E by the way, I don't know if I drew that very well, are going to migrate to here, the p-n junction. The holes, obviously when that happens, holes are going to move that way, aren't they? If you have more charge here, that's going to basically have the effect of moving the barrier this way. So the net effect is your p-n junction is going to widen. Okay? So the p-n junction will get wider. Okay? Now look, it's going to get wider, and as you have more charge, as you have more electrons here and more holes or positive charge here, you're going to have greater potential. So it's going to increase until it reaches equilibrium. At equilibrium, there's no more flow of charge carriers, okay? So it's going to meet the voltage that's put on it, all right? That's an important thing to remember. Now look, there is a reverse current. This is due to minority carriers in the N and P regions, all right? It's a very small current, but minority carriers in the P region, which are electrons, are pushed toward the p-n junction where they fall down the energy hill to the p-type region where they combine with holes and flow toward the positive bias. But remember, those are the minority carriers. Remember, the majority carriers in the N region are electrons. The majority carriers in the P region are holes. All right? The minority carriers in the N region are holes. The minority carriers in the P region are electrons. Okay? So there is a little current flowing, but there is not a significant amount. It's very small. Now look, when the reverse bias voltage is large enough so the minority carriers collide with free minority carriers, this is when you have a problem. But they're going to have enough energy. If your reverse voltage is large enough, they're going to knock them out of the valence band into the conduction band. And they're going to hit others, which are going to knock out of the valence band in the conduction band. And what you have is a cascade or avalanche of electrons. When this occurs, you have reached the point of breakdown. Okay, at this point, you're going to have current flow, and if you keep going, if you exceed that reverse breakdown voltage too much, it's going to get very hot and you're going to destroy the diode. What keeps this from happening is this resistor right here. Remember, from Ohm's law, V equals IR, right? So V over R equals your current. You have control of this and you have control of this. So with both of these values set, you can limit your value of current. Okay? All right, everyone, I hope this has helped in your understanding of the diode, and I will see you again soon.